So here we go. The natural numbers are just the counting numbers. If I say natural number, you're thinking about the set 1, 2, 3, 4, 5, and so on. Infinitely many natural numbers. And sometimes we also include 0. It kind of depends on context, whether or not we're talking about 0. This symbol, that's called a double-struck N. And it's a historical remnant of the past where people used to type math out on typewriters. And to make this symbol, you would hold the register and you hit N twice on your typewriter. So it would strike the page twice. So double struck N is a symbol we use for the natural numbers. These little curly brackets, they tell you that we're talking about a set of numbers, and the ... means it keeps going. When I talk about an operation, this is a really, really vague vocabulary word. It could mean we're talking about addition, subtraction, multiplication, division. It might actually mean that I'm talking about taking the square root of a number. I might talk about the cube root of a number. An operation is, like I said, very poorly defined word that, again, depends on context. So these are our first questions. Is the set of natural numbers closed under addition? What I mean by this question, it sounds really funny. What I mean is that if you take two natural numbers and you add them together, is the result going to be a natural number? Yes, absolutely. It doesn't matter which two numbers you choose. You choose two natural numbers, add them together, you're going to get another natural number back. Is the set of natural numbers closed under subtraction? You said yes? Anybody else? No. We got our bases covered. It is actually no. So the reason is some work, like 5 minus 3 works. It gives you a natural number. But 3 minus 5 gives you -2. And -2 doesn't belong to my set of natural numbers. So it doesn't always work. It means we're not closed under subtraction. This is something that first graders think about a lot in their math class. If you ever ask a first grader, what's 3 minus 5? They'll tell you it doesn't exist. You can't do that. First graders are really only aware of the natural numbers. They don't really think about integers until a little bit later. Is the set of natural numbers closed under multiplication? Who says yes? Who says no? Okay, so the answer is yes. To remind you, the set of all the natural numbers are just positive integers and 0. And if you multiply any two of those, you're going to get another natural number that belongs to that set. Okay? The next question I would ask is, are the natural numbers closed under division? And who thinks yes? Who thinks no? So 3 is a natural number. If I say 3 divided by 5, this is not a natural number, right? And so the answer is no, we are not closed under division. Closed under division would mean you divide any two natural numbers, you get a natural number. That's not always the case. Okay. if I wanted to multiply two large natural numbers like these, the big numbers, I'm not allowed to use my calculator. So what I would think about is how 513 is the same thing as 500 plus 10 plus 3. So I've got this line segment and the length is 513, but I could chop it up into 3 pieces where the lengths are 510 and 3. And I could do the same thing with 17. I could say 17 is the same thing as 10 plus 7, and break that line segment that has length 17, break it into 2 pieces. And now multiplication is just the problem of finding the area of this rectangle. And what I would do is find the area of all of these little boxes. And if we do that first, it's pretty easy to find each of those little areas separately. And to get the total, we just add them up. So it would be 5,000, 8,500, 8,600, 8,670, 8,700, 8,721. That's how you do multiplication.
Isn't that lattice?
I don't know what it's called. Sorry. It probably is. This is just what I do. So, we're going to do multiplication with other things later this semester. Like, I don't want to spoil the surprise, but if you had something like this, something that looks more algebra-y, and I want to multiply those two expressions, the way that we're going to handle this is, say, draw a rectangle. I'm going to break up this side of the rectangle into line segments with these lengths and do the same thing on that side. And it's so easy to just multiply those terms individually, like what I'm doing now. And to get your result, you would just add all those together. And so we'll do this again several weeks from now, maybe like 3 weeks from now, 4 weeks from now. Plus an x squared, so that should really be 4. After that, plus that, and then plus 3. But the kind of same method that you use for multiplying numbers also applies to other things. In fact, lots of things in algebra. We'll want to use this moving forward to keep our work straight, nice and organized. So moving on, we've got exponents. Whenever I see this, a big 3 with a little exponent 4 on top, we read it out loud as 3 raised to the power 4. And the way you calculate 3 raised to the power 4 is 1 times 3 times 3 times 3 times 3. So I got 4 copies of the number 3. And we multiply. So it helps you remember, a little 1 there helps you remember that if you've got 0 raised to some power, this is like 1 times 0 times 0 times 0 times 0 times 0. That's just 0. You multiply by 0. So 0 raised to any power is 0. Doesn't matter what power is up there in the exponent. What about anything like the number 4 raised to the 0 power? Well, that would be 1 times how many copies of the number 4? 0. Yeah, so that's why anything raised to the power of 0 is just 1, even if the base is like 2024, raised to the 0 power is still 1. Once again, 0 raised to the 0 power is also 1. We probably don't have to worry about that a lot, but if you were curious. 0 to the 0 is the number 1. So, question for you again. Would we say that the set of natural numbers, if I have a natural number base and a natural number exponent, is that closed under exponents like this?
Yes.
Yep. It is, because really all we're doing is repeated multiplication. And the natural numbers are closed under multiplication. And so if we just do that a bunch, we're also closed under exponents. Okay, so we can talk about multiples, new vocab word. If I ask you for the set of multiples of 7, what I'm talking about is 7 times the set of all the natural numbers. We got 7 times 1, 7 times 2, 7 times 3, 7 times 4, and so on. I know you're probably familiar with this stuff, but I like to say it at the start of the semester, just in case. If you've got multiples of 2, we also call those the even numbers. And if you happen to have a natural number that is not even, it automatically belongs to the odd numbers. Even and odd numbers follow very rigid rules when it comes to arithmetic. So if I were to add an even number plus an even number, what am I going to get? An even number. What if I add an odd number plus an odd number? All right. I'm glad there's a little disagreement. It means we're learning something. It's going to be even. What if I have an even number plus an odd number? Odd. And then addition, it turns out it doesn't matter what order you add things in. And so whether I do even first and add odd, or odd first and then add an even, both are going to turn out odd. With that property, whenever the order doesn't matter, we call that the commutative property in math. So you may have heard addition is commutative before. What about multiplication? If I do an even number times an even number, I get even. What if I do an odd number times an odd number? Odd. Even times odd? Even. And what about odd times even? Yeah, it doesn't matter. We also say multiplication is commutative because it doesn't matter the order in which you're multiplying numbers. Okay, an even number base raised to an even number exponent. Even. What about an odd number base with an odd number exponent? Odd. What about an even number base with an odd number exponent? Even. And what about if you had an odd number base with an even number exponent? Odd. So the trick to this, you do not have to memorize this table. This is the trick. The rules work for every even and odd number. So you can choose the easiest even and odd numbers to think about. I like to think about 2 and 3. So I think about what is like 2 plus 2? Oh, it's 4, that's even, you know. What is 2 raised to the third power? That would be, oh sorry, right here. 2 raised to the third power, that would be 8, that's even. You know, 3 raised to the 2 power, that's 9, that's odd. You can just use 2 and 3 as placeholders for even and odd. And since it has to work for all the numbers, it has to work for 2 and 3, and that's the only thing you have to remember. But I just want to point out that they follow patterns, you know. All right, we use the word divisible. If you can take a natural number and divide it by some other natural number, and the quotient is a natural number. And that's not always true, because the natural numbers aren't closed under division. Like, for example, is 16 divisible by 5? Nope. That is not natural. Is 21 divisible by 3? Yeah. How do we know if a number is divisible by 2? Yes. That is the definition of even, is that it's like a multiple of 2. But if I were to look at this number down here, what do you look at when you're trying to decide if it's divisible by 2?
The last number.
Yeah. I only care about the last digit. So forget the 5 and the 9 and the 3 and the 8. It doesn't matter. The only thing that matters is whether that last digit is 0 or a multiple of 2. So in this case, yeah. 8 is divisible by 2, so we're good to go. And we know that it is. How do we know if a number is divisible by 5?
8 ends in 0, 5.
Exactly. You only care about the last digit. If it's 0 or 5, that's how we know. This is just a consequence of our base 10 counting system. 10 itself is divisible by 2 and 5. And so everything else in the number that's not in the last digit is a multiple of 10. So of course it's a multiple of 2 or a multiple of 5, and so we don't have to worry about that. How would we know if a number is divisible by 3? There's always like one person that knows this. I bet you've seen this before. I bet we just forgot. You just add the digits. So here I would say, what is 7 plus 5 plus 5 plus 8 plus 3 plus 9 plus 2?
39.
Is it 39? For some reason I was remembering 36, but you might be right. I haven't done the math. Yeah, you're right. That's 39. Very good. Then I can say, well, 39, add those digits. Add those digits. Whenever you're done adding the digits together, if you have a 3, a 6, or a 9, if you have a multiple of 3, then you're good. The original number was a multiple of 3, or divisible by 3, right? So the answer to this question is yes. It's divisible by 3 because whenever I added the digits together, I got something that was divisible by 3. The reason that works is, again, because of the silly base 10 system. 10 is not divisible by 3, but it's just one more than 9. And 9 is divisible by 3. So every single time you see something like this, we're counting the number of extra little ones we get on top of the 9s. Right, like 2, because 2 is in the final digit, but we get 9 because there's 9 copies of 10 in 90, and 10 is just 9 plus 1. So what we're really counting is how much are we above a number that is divisible by 3. And this 3 in my sum right here represents 3 copies of 100, right? Because it's the 300 part of 392. And 100 is just 1 more than 99, and 99 is divisible by 3. Likewise, this 8 stands for 8,000, and 1,000 is just 1 more than 999, which is divisible by 3. So every single time you're just counting these little awkward ones that pop up. And that's why the add the digits trick really works. The same thing works then for 9s. So if I want to know if a number is divisible by 9, we add the digits. Like this, what is 2 plus 2 plus 6 plus
36.
That's where I was thinking the 36. It came from this question then. 3 plus 6 is 9. So if you get a 9, then you know, yes, this number is divisible by 9, because I added the digits and I got 9 at the end. Same exact reasoning, same explanation. So the notable, really, really difficult cases is if you're asked, is it divisible by 4? You're out of luck. You're screwed. 6, 7, 8. You would have to actually do long division to the number and see if you have a remainder. It's not like a fast trick. Do you have a question?
Well, we have access to these notes as you're online.
Yeah. Yeah, like I said, I'm taking a recording of this and I'll just post it on this page so you can go back. If I'm going too fast and you can't take notes on everything you want to take notes on, you can also just go back, watch that recording later, and you can catch it. Yeah. Okay, about halfway done here. A natural number is a prime number if it's not divisible by any natural number other than 1 in itself. So that's what we call prime. It doesn't have any factors. A natural number is a composite number if it's not prime. So a number is either prime or composite. It's got to be one or the other. Because composite just means it's not prime. Is 36 a prime number?
No.
No? So we say, oh, I said 36. 39. 39 is composite.
13.
Is, yeah, 3 times 13. Is 17 a prime number?
Yes.
Yes, it is. Nothing divides 17. Is 127 a prime number? This is how we check. I don't know. That's a big number. I don't know if it's prime or not off the top of my head. So we could ask, is it divisible by 2? No, because the 7 isn't divisible by 2, and we only have to care about the last digit. Is it divisible by 3? No, because the digits add up to 10. I don't have to worry about 4 because it can't be divisible by 4 if it's not already divisible by 2. And for that same reason, you don't have to worry about any factors except for prime numbers when you're trying to test if a number is prime. So we can skip the 4 and move right on to 5. Is it divisible by 5? No, we just check the last digit. Is it divisible by 7? It might be, and this is a pain. This is a pain to check. So one thing I can think of is 7 times 20, what's that? 140. That's pretty close, so let's try 7 times 19. That would be 133. What about 7 times 18? 126. Okay, so the answer is no for 7. That was more difficult to have to sit here and check, but we still know it's not. We don't have to worry about 8 or 9 or 10 because those aren't primes. What about 11? Is that divisible by 11? No. I say that because 11 times 11 is 121. 11 times 12 is bigger than 127. Okay. I spoiled the surprise because my question's already on the board. We don't have to test whether or not 127 is divisible by 13. That would be the next prime we check. You know, we would ask ourselves, is this 127 divisible by 13? But we don't have to because 13 squared is 169. 169 is greater than 127. If 127 was divisible by 13, there's 3 ways this could happen. Either it's 13 times 13 equals 127. It's not. Or 13 times a smaller number is 127. That's possible. Except we already tested all of the smaller numbers already, so we ruled it out. The last possibility is that it could be 13 times a larger number is 127, but 13 times a larger number would be even bigger than 169. So that's not possible. So we can stop testing once we reach a number whose square is bigger than the number we're trying to test out. Okay? So since 13 squared was bigger than 127, we can stop and we don't have to keep going. We don't have to wonder about 13 or 17 or 19 or 23 or anything like that. And the answer to the question is yes. We verified that. So here's a new kind of question. When I ask you this semester to find the factor pairs, this is what I'm talking about. You say 1 times 36, that's a factor pair. 2 times 18, that's a factor pair. 3 times 12. 4 times,
Oh, shit.
9, it's close. 5, doesn't work. And 6 times 6. I call these factor pairs because they're obviously pairs of numbers, and when I multiply them, I get 36. We'll do one more and move on. 42 would have factor pairs 1 times 42, and don't forget the 1 times 42 bit, because that'll be important later. 2 times 21, 3 times 14, 4 times, doesn't work. 5, nope. 6 times
8, 7,
7. So there's 4 factor pairs in this case. And that's all of the factors of 42. Each one of those 8 numbers is a factor. Together they make factor pairs. Now, new type of question. Let's find the prime factorization of 210. 210, is it divisible by 2?
yes.
Yes. It's 2 times 105. Is 105 divisible by 2? Nope. Is it divisible by 3?
Yes.
1 plus 5, 6? Yes. 3 times 3 times what gives me 105?
15. $35.
35. Very good. Yeah, you kind of have to try some things out. Like 3 times 30 is 90. That's too small. 3 times 40 is 120. That's too big. Got to kind of do a Goldilocks scenario in your head until you narrow it down. Is 35 divisible by 3? Nope. Is it divisible by 5? Yeah, 5 times 7. Cool. Now these numbers are all prime numbers. And that means I'm ready to write my prime factorization. I say that 210 is equal to 2 times 3 times 5 times 7. And that's it. That's what I call a prime factorization. Let's do the same thing for 360. Is it divisible by 2? 180. Is 180 divisible by 2?
Yes. 90.
90. Is 90 divisible by 2?
Yes. No. Yes. 40.
Is 45 divisible by 2?
No.
Nope. Is it divisible by 3?
No.
Is 15 divisible by 3?
Yes.
Cool. So now again, I'm at the point where I have all prime factors. And the way I write this prime factorization is like 2 raised to the 3rd power, 3 squared times 5. So I've got 3 copies of 2, 2 copies of 3, and 1 5. Questions yet? Okay. So the greatest common factor. Greatest common factor is kind of an annoying thing to describe. What it is if you've got two different numbers and you write out all of their factor pairs like we did a moment ago so you can see what their factors are. If you look for the largest number that belongs to both lists of factors, that's what we call the greatest common factor. You could write out the factor pairs, and you could find which number is the biggest number in both lists. That's a valid way to do it. There's another way of doing things that I sort of prefer. And what we do is we find the prime factorizations first, and then we select the smallest power. So, prime factorizations of these numbers would be like 2 and 63, 3 and 21, 3, 7. This is not divisible by 2, but it's divisible by 3 and 7. Okay. So, I'm gonna scooch that over. I shouldn't have written it. I'm taking up the whole screen. This is going to be 2 times 3 squared times 7. And this is going to be 3 times 7 squared. What is 7 raised to the 1 power? 7. So if I go ahead and I drop in a few 1s in the exponents here, it doesn't really change anything. It's still valid. What would be 2 raised to the 0 power? 1. Anything raised to the 0 power is always 1. So in this case, I've got 2 raised to the 0 power. That's like 1 times everything else. But it doesn't really change the number if you multiply by 1. It's still the same value. And so that's also a valid thing you can do. The reason I want to do this, I just want it to look more filled out, I guess, a little bit more organized when I try to find my greatest common factor. Because what I'm going to do here is select the smallest power of each prime. So for my 2, what's smaller, 1 or 0? 0. For my 3, what's smaller, 2 or 1? 1. And for my 7, what's smaller, 1 or 2? 1. That's exactly what I mean when I say select the smallest power of each prime. That's what I'm talking about. So 2 to the 0 power, that's just 1. 3 to the 1 power, and 7 to the 1 power. My greatest common factor is 20. Does it make sense, what we just said? Okay. Let's talk about least common multiple now. So the definition of least common multiple is you start off with 2 numbers and you make a long list of multiples for both numbers, right? So the way this might look is like I say 126. 252, 378, and on and on and on. And I say, okay, 147, 294, 441, I don't know. And so you make these long lists of multiples and you try to look, what's the smallest number that belongs to both of these lists? Would be the least common multiple. The slightly faster way of doing things is that we're going to find the prime factorizations and then select the largest power of each prime this time. So it feels backwards, Because for greatest common factor, we choose the smallest power, but for a least common multiple, we actually choose the biggest power. And so between 1 and 0, I'm going to choose the 1. Between 2 and 1, I'm going to choose the 2. And between 1 and 2, I'm going to choose the 2. So I've got 2 times 9 times 49. So we're talking like 9 times 98. So this would be 882. You'll notice least common multiple is always larger than the greatest common factor. Really quick, just in case anybody needs another example, we can run through a quick example. We have already found the prime factorizations of 210 and 360. Earlier in this lecture, we found these prime factorizations. So the greatest common factor is what I get when I look at those and I try to think, I'm going to choose the smallest powers for the greatest common factor. The smallest powers would be 2 times 3 times 5. Right? 2 to the 1 power, 3 to the 1 power, 5 to the 1 power. And then 7 to the 0 power. Right? The least common multiple is what I would get if I chose the largest power every time. So we're talking about 30 and something large, some big number. We could practice our multiplication skills really quick. We're talking about 72 times 35, right? So pretend you're finding the area of this rectangle. And this would be 2,450, 2,520. Are there any questions about GCF or LCM before we move on?
On the GCF, can you just use like the, for example, like the example, what you use to see if it's divisible by 3 and how you add them up? Is it possible to do that to find the GCF?
I don't think so. You can check to see if it's divisible by 3 for each of one of these numbers,
Yeah.
and you would know that 3 belongs to your prime factorization.
But you wouldn't know how.
And that is a step. I mean, you've got to find the prime factorization first before you can use this method.
Mhm.
But it would just be like the first step towards doing it. So you can do this with 3 numbers as well as just 2 numbers. Like if I ask you about 6, 15, and 21, 6 has a prime factorization 2 times 3. 15 has a prime factorization 3 times 5. And 21 has a prime factorization 3 times 7. So again, when I find the greatest common factor, I'm looking for the smallest little exponents. The smallest exponent on 2 is 0, because it's missing in some of these. The smallest exponent on 3 is just 1. The smallest exponent on 5 is 0, and the smallest exponent on 7 is also 0. So the greatest common factor here is just going to be 3. For the least common multiple, I'm actually looking for the greatest exponent on each one. which is just 1 all the way down.
I mean, I guess that question I just asked you kind of answered itself with that one. Like I used the,
Yep.
the 3 divisible on it.
Oh yeah, because you saw they're all divisible by 3. That only works, you know, if they don't have any other things, other factors that are also divisible by, you know. All right. So, almost done here. We've got integers. Integers have a symbol that's internationally recognized, the double-struck Z. And I wrote it kind of silly in my notes. But this is the set of all of the natural numbers. We always include 0 when we're talking about the integers. And it's also all of the negative natural numbers. So it kind of goes out to infinity and negative infinity in both directions. And some of this I've already asked you, but I'm going to ask you again just to refresh your memory. Are the natural numbers closed under addition? Yes. Are the integers closed under addition now? In other words, if you have one integer and you add another integer, you add 2 integers, are you going to get an integer back? Yes. Always, 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 no matter what your 2 integers are, you add them together, you get an integer. Are the natural numbers closed under subtraction? Nope. We talked about that. 3 minus 5 does not exist. Are the integers closed under subtraction? Yes, because 3 minus 5 in the integers gets to be -2, and that's an integer. Are natural numbers closed under multiplication? Yes, they are. Are integers closed under multiplication?
No.
Yes, they are.
Or would you just get positive? Negative, negative?
Yeah, so the integers is not just negative numbers, though. The integers contain the negative numbers and the positive numbers. Yep, so if you multiply 2 negatives, you still end up inside the integers, so we can say yes. Are the natural numbers closed under division? Nope. What about integers? We closed under division? Nope. The negatives there like don't save us from situations like that, which is not an integer. Okay. Is the following sum positive or negative? Negative. How do you know? Yeah. If you're adding together a negative and a positive, if the negative is bigger, then it's going to end up negative. This then would be positive. Okay. Is this going to be positive or negative?
Negative.
Why would this be negative?
There's 3 negatives.
Yeah, it's always going to be negative when there's an odd number of minus signs. What about this?
Positive.
Yep. Your product, if you have a whole bunch of factors, is always going to be positive when we have an even number of minus signs. Or if you don't have any at all, that's good too. -7 squared, positive or negative? Positive. Yeah, because if I expand that out, -7 times -7, that's an even number of negative signs. This would be negative because 3 is odd. This would be negative because 7 is odd. And that's positive. Very good. Last question of the day. How many prime numbers are there? You said? Infinity? How do you know there's infinitely many? Yeah, there are an infinite amount of natural numbers, right? You keep counting forever. But what if What if there was a certain point where you just ran out of primes and the rest of the natural numbers were all composite numbers? Is that possible? So you guys I think are right. The answer, how many prime numbers are there? There are exactly 73. I'm just kidding. There are infinitely many prime numbers.
I don't think anybody says.
Yeah. Okay. There are infinitely many primes. How do we know? How do we know the prime numbers don't just stop at like 3 trillion and then there's no more primes, it's all composites, right? That's a possibility. Like you said, that's actually one possible way things could turn out. So the way we know for sure is we start off by playing the devil's advocate. I say, I'm going to go ahead in this, speech and debate drill. I'm going to take the opposite side and see where we go. I'll say, suppose there are a finite number of primes. I'm using lowercase n to just represent a number. It could be really, really big, right? It could be 300 trillion. But it's just a number that's not infinity. Suppose there's a finite number of primes. Then we could label them. This is what I mean by labeling them. The number 2 would be my first prime. The number 3 would be my second prime. The number 5 would be my third prime. The number 7 would be my fourth prime. And labeling these primes, we would eventually get to the biggest prime. And since there are n, that's my big number, primes, I would label this one Pn. The nth prime is the biggest prime. Okay? So now we're going to define ourselves a new number. We're going to call it x. My number x is going to be equal to the number 2 times 3 times 5 times 7 times all of the primes, however many there are, times the biggest prime plus 1. Okay? Now, x, this number is not divisible by 2. I know this is true because if I just underline this green part here, that underlined part, that is divisible by 2 because 2 is a factor. But when I add 1 to the end, I mess it up, right? Like if you take an even number plus 1, you get an odd number. It's not divisible by 2 anymore. What about 3? X cannot be divisible by 3 because this green underlined part is divisible by 3. You could divide out that 3. But then x means I take that and I add 1 to it. So think of any multiple of 3, and then you add 1 on top. Now it's not a multiple of 3 anymore. So we're not divisible by 3. X is not divisible by 5 for the same reason. The green underlined part is divisible by 5 because of that 5 factor. But then, to get x, I have to add 1 and mess it up. So it's not divisible by 2, 3, 5, 7, or any prime. And that means x is a prime number. We also know that x is greater than the biggest prime. Because we've got 2 times a whole bunch of other stuff, times the biggest prime, plus 1. I mean, x is definitely larger than the biggest prime. So what we know so far, Pn is the biggest prime number. X is a prime number, and x is bigger than the biggest prime number. That's what we call a contradiction. So at this point in our proof, we say, we have found a contradiction. And if you find this kind of logical contradiction, you have to ask, what went wrong? Everything we did was completely logical, completely airtight. We didn't do anything wrong with this proof. So the place where we went wrong was this hypothesis. The second you try to assume that there's only a finite number of primes, you end up with a logical contradiction. So that's what we call proof. We have just proved that there must be infinitely many primes. There's not a point where they just turn all composites. Even though it seems like it might be possible. And that's it. So you guys are free to go. You can take back your 12 minutes and enjoy the rest of your day. Work on that homework, and I'll see you guys again on Wednesday.